Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to be talking about how salts can act as acids or bases. So most of the time when we're thinking about acids or bases, we're thinking about charge neutral compounds, such as acetic acid or ammonia. However, it turns out that most acids and bases tend to exist as cationic or anionic species, which makes sense because for every neutral species, there's going to be a charged conjugate. So for example, acetic acid generates the conjugate base acetate, who is going to be negatively charged, and with that extra negative charge can go out and grab a proton. Similarly, ammonia can generate the conjugate acid ammonium with its plus charge and one more proton than is good for it, can act as a weak acid. However, we also have things like perchloric acid, which can decompose to form perchlorate. So this is going to be our conjugate base. However, we also have much more nuanced scenarios like dihydrogen phosphate. Turns out this is going to be a base because it's the conjugate base of phosphoric acid, but as we saw last lecture, turns out it's also an acid. Makes things real fun. And then we have things like carbonate, which is negatively 2 charged and is a diprotic base. However, one of the things is when we're looking at all these various charged species, it's important to remember that they never occur in solution on their own. Every solution needs to be charge balanced. So for every anion present in solution, we need to have a cation. And for every cation, there has to be a corresponding anion. So most of these ionic acids and bases are going to be occurring in nature as salt. And a lot of these will be fairly familiar to you. So this includes things like sodium acetate, which if again you look at your food labels, you'll find is a very common food additive, and mostly because it acts as a nice preservative. So it is acetate with a conjugate sodium cation. Turns out that acetate possesses a pKb of 9.25, so it's a decent weak base. And as a result, if I go ahead and put sodium acetate in solution, the solution's going to go basic because I put a weak base in water. We know how to calculate that pH. On the other end, we can have things like ammonium nitrate. So this is one of the world's most common fertilizers, as well as being slightly explosive when ignited, and has been in the news several times over the last 10 years for causing disasters in ports where there's too much of it. Well, the big feature here is that ammonium is going to be a weak acid, and it turns out it possesses a pKa of 9.25. No, this is not a typo. It turns out that acetate has the same pKb as ammonium has a pKa. It's just one of those odd mirror images. But as a result, it turns out that if I throw ammonium nitrate into water, which is going to be quite common when we're adding a fertilizer, it's often going to be dispersed in water, it's going to generate a net acidic solution, which can actually cause a lot of issues when farming. So you'll often need to put in a base in there to keep the pH neutral to help out the plants. And it turns out that we also have just a lot of salts like the sodium dihydrogen phosphate. It is both a base and an acid. And these species are called amphiprotic. And we're going to spend a lot more time on them in the next chapter. But one of the big things is we can go ahead and get a rough idea of the acidity of a species by looking at its pKa's and its pKb's. So phosphoric acid has 3 pKa's and the corresponding pKb's. So if I'm looking at hydrogen phosphate, we'd be looking at losing our second proton or gaining our third proton. So what we're really going to be doing is comparing pKa2 to gaining your third proton, pKb3. And you're going to notice it's going to have a stronger pKa than pKb. So it turns out this is going to be a slightly more acidic than basic. However, don't worry about this too much. We'll spend a lot more time on this next chapter, but it does end up emphasizing the point. There's a lot of acid-base behavior that can occur in these complex salts. So as you're going to try and look at a salt and figure out whether it's acidic or basic, one of the big things we need to do is keep in mind which anions are going to and cations are going to be a base or an acid. So we're going to use a couple of rules to guide us along. So the first of which is any conjugate base of a weak acid is going to be basic and produce a basic solution. So this means that if I have something like acetic acid, acetate is going to be a weak base. So if you put acetate in solution, it's going to be basic. Similarly, hydrofluoric is a weak acid. So this means if I put fluoride in solution, it's going to act as a base, as it's going to consume the extra protons, generate some extra hydroxide. Similarly, hydrogen cyanide is a weak acid, which means that cyanide is going to be a weak base, again, driving the reaction in reverse. However, this also happens when we're looking at the conjugate base of an acid. Sorry, the conjugate acid of a base, like ammonia. So ammonium will produce ammonium. So this ammonium, if put in solution, will be fairly acidic and can drive the reaction to the left. Now, one of the other things you have to watch out for, again, is these polyprotic species. They may have acid or base properties, or in the case of dihydrogen, monohydrogen phosphates, and bicarbonate, it can have both. And we'll talk about how to predict these pHs much later. Now, the last ones you should keep in mind for an eye out for is going to be the conjugate bases of strong acids and the conjugate acids of strong bases. So if I'm going ahead and looking at the conjugate base of a strong acid, so for example, hydrochloric acid is a strong acid. This means it completely breaks apart to release protons and chloride. As a result, it turns out that chloride cannot grab a proton. As a result, chloride isn't going to be a base. These form what are called neutral salts, which is a bit of a misnomer because salts have to be charged, but the neutral in this case means that they generate a neutral pH. So these are going to be any of the salts that are the conjugate bases of a strong acid, most notably chloride, bromide, iodide, nitrate, chlorate, and perchlorate. So perchlorate, while it is a base, is so bad of a base that it can't actually grab a proton. It's mostly a base in name rather than function. However, you will notice that there is one conjugate base of a strong acid that we dropped out. That's monohydrogen phosphate because it's polyprotic. So it belongs in its own category. Otherwise, these are going to be the species that are the classic counterions for most salts because they have no acid-base properties. Similarly, if I have the conjugate acid of a strong base, it's not going to have no acidic. It is not going to act as an acid. So for example, sodium hydroxide is a strong base because it completely breaks apart to form sodium and hydroxide. That means that sodium can't just go into solution and pick up a free hydroxide and send the reaction in reverse. So it's going to be not acidic at all. And so as a result, lithium, sodium, potassium, calcium, and barium are often referred to as neutral salts as well because they won't produce any protons or hydroxide if put in solution. They more or less don't influence the pH. So this is the reason why you can pretty much throw sodium chloride into solution to your heart's content, and the pH of water won't really change. However, the same won't be true if you start throwing in weak acids or weak bases. And it turns out that some metals can actually have some odd acidic functions, which we'll talk about next time with Lewis acids. Until then, take care.